lucky to have Jenny Nelson here today to give us a seminar. And just to give a brief introduction, Jenny is a professor of physics associated with the Department of Physics, as well as the Grantham Institute for Climate Change at the Imperial College of London. And she's an expert in solar cells. She literally wrote the text on it, and I have used this in my course, particularly for the treatment of detailed balance, which I find to be very, very nice, very compact. She's also the recipient of the 2016 Institute of Physics Faraday Medal and elected a Fellow of the Royal Society in 2014, one of the highest honors in Britain. And without further ado, we'll have her tell us about her recent work in molecular electronic materials that I know a lot of us are interested in, particularly the structure, property, function relationships in molecular electronic materials and devices.
Okay, Barry, thank you very much. Can people hear me okay? Sounds a bit fuzzy to me. It's all right? It's good. Okay, so thank you, Barry and Andlinger, for the invitation to come here. It's a bit frightening for me, but I'll probably get over it. And it's my first time to visit Princeton, so this is a pleasure, and I've had a very nice time over the last 24 hours meeting faculty and students and hearing about what's going on here. So, as Barry said, I have two positions. I'm mainly employed by the Department of Physics at Imperial College London, and I'm also attached to the Grantham Institute for Climate Change. And it's very fuzzy. I might use a podium mic. Is this on? No, it's not. Okay.
If you'd like to, I can turn it.
No, it's just I'm hearing a lot of feedback, but I don't know if other people are.
We are not.
You're not. Okay, that's fine. It's only my problem. Okay. Why are we here? So when we look at what needs to be done to avoid the most dangerous effects of climate change, and this is a study we carried out in collaboration with the Met Office in the UK and the Grantham Institute a year or so ago. We made an evaluation of how rapidly we would need to decarbonize to reach a trajectory that would be unlikely to exceed global temperature rise of 2 degrees centigrade. And looked at, using integrated assessment models, a variety of models, which technologies would need to be picked up to reach those targets. And if we were to take serious action from 2020, which is now not so very far away, we would be looking at a sizable increase in various low-carbon technologies, some of which are proven, some of which have yet to be proved. If we were to delay and not take action until 2030, then the rate at which some of those technologies would be picked up would be greatly, the degree to which some of those technologies would be picked up would be greatly enhanced. And if you look at what's happening over here in the last column, we have solar power. And you can see that in the case that we delay too long, and then again, although it's not written here, it's obvious in the case that some of the other technologies fail to deliver to the extent to which we would like them to, solar is going to become an absolutely critical part of the future energy mix. And for that reason, many of us have got a strong focus on solar power amongst renewable technologies and looking at what it might do in order to help us meet the demand of changing our energy system to one that's compatible with low carbon emissions. So in this kind of context, I work with the Grantham Institute. We do this type of modeling. And I also am working with some of the groups in Imperial College who are investigating different types of solar energy conversion. Most of our activity is in photovoltaic materials, and that involves basic physics and chemistry. We also have some activity in the demonstration and evaluation of technologies. And we also have a growing activity in use of materials for photocatalysis, and some of my colleagues also interested in solar thermal as well. And so this kind of family of energy technologies is something that we try to evaluate the relevance by talking with the people who are interested in policy and sort of energy futures in the Grantham Institute. And in this context, we could ask the question, where does material science come in? And so if we think about what are some of the research issues for energy technologies of the future, we can think about cost, we can think about what potential there is for innovation, and we could think about also the energy cost of the materials and the scale at which they could be developed. And then these are all things which are to do with the technologies themselves and can be very much to do with the materials. And then on the other hand, there are system-related issues like the variability, the complementarity, the response rate, and to some extent the product form. But if we think about the kind of the issues that are basically to do with the efficiency with which our system and the materials within it can achieve the goal of converting one form of energy to another, there is a huge amount of work, science work, that needs to be done to optimize the business of relating this function to materials and processes. And amongst the energy technologies that are relevant here, we find PV as well as other solar thermal, solar chemical, and other conversions and other conversion mechanisms. So that's kind of the context in which I want to introduce, but not overstate, the material system that we're working with. So, as Barry said, for the last 15 years or 10 to 15 years, I've been working with molecular semiconductor materials. And here, I mean, I'm speaking about semiconductors which are based on light elements, primarily on carbon atoms, which are hybridized in the sp2 configuration. And as such, a network of such atoms gives rise to an electronic system composed of the most weakly bound pi electrons, and they give rise to the frontier electronic orbitals of the system, which are occupied or unoccupied, and give rise to properties that are similar to those of a semiconductor. They give rise to the possibility of absorption and emission of visible photons of light. This, of course, is relevant to solar energy capture and conversion, and they give rise to a certain degree of electronic conductivity, which gives rise, which enables electronic properties. So we're interested in these kind of semiconductor materials, and why? Partly because of the very low cost, if you like, in terms of the materials that are used, their availability, and the intensiveness of the processes that need to be used to manufacture and process the materials into semiconductors. Partly they're interesting because of their tunability, and partly they're interesting because of the huge variability in microstructure, which then leads to a lot of flexibility in the product form. And I'm going to be talking mainly about the application to solar energy conversion, but such materials are also relevant to light emission, which is another place where we have a target of trying to save energy, and can be relevant to other energy-related devices in thermal energy conversion, in sensing, and so on. So what I'd like to do now is to kind of take a short tour through some of the properties of molecular semiconductor materials and how they differ from inorganic materials. And we can start by saying, if you're an electron and you look inside a crystalline semiconductor, such as silicon or gallium arsenide, then what is present is a very ordered environment where the periodicity of the atomic structure gives rise to extended electronic states, and your charges may occupy an extended state in conduction band if it's been excited in the valence band. Taking a look inside a molecular semiconductor, then we see immediately that the environment is somewhat more disordered, and the states that can be occupied by our electronic charges are necessarily localized in their extent, partly because of the sort of strong coupling between the electronic and vibrational degrees of freedom of the system, and partly because of the intrinsic disorder, which comes along with the soft nature of the material, which is also the property that makes them easy to process. So the thing which makes them attractive is also something which makes them difficult from a design point of view. And then when we look at the nature of electronic transport, in the case of our extended material, transport is relatively facile. In the nature of our disordered material, transport is obliged to occur by a series of incoherent, normally, hops from one localized state to another state. And this can be described effectively with some hopping theory effectively based on Fermi's golden rule. So we have a different nature of electronic transport in the two systems. Not only that, if we look at the nature of a photoexcitation, so in solar energy conversion, you want to absorb a photon and generate free charges. This happens relatively spontaneously in an inorganic semiconductor. And in the case of our disordered semiconductor material, which also, because of the low molecular weight of the atoms involved, has a low dielectric constant, we tend to generate a state which is locally bound, where the electron and hole are tied together, and a relatively high degree of energy, a relatively large amount of energy is needed to liberate the charges and allow them to move freely. That creates a problem for solar energy conversion. The classic picture of a photovoltaic device is something where you can create, by using two electronically different electrodes, a driving force to encourage an excited electron to move in a particular direction, and then give rise to a directionality in the photocurrent. We can't do that in something where the excited states look like this, because a driving force at an electrode some far distance away from this excitonic state will have no impact on what happens to the liberated, to the charges that are bound there. We need first to liberate the charges, and that's typically done by using this device of a heterojunction, where a second material with a higher electron affinity attracts the electron away from the exciton, and then, having done that, this heterojunction can be embedded in a device where you have electronically different electrodes, not now created by doping, but by using different work function metals, and that then provides the direction that we need for a photocurrent. So when we put that together into what is now kind of the model of, or sort of the best studied model for photovoltaic energy conversion in organic semiconductors, which is called a bulk heterojunction or a dispersed heterojunction, we have our two semiconductors mixed together in some way that may be controlled, we'll come to that later, between two electronically different electrodes. And the sequence of stages that then proceeds is we will somewhere absorb a photon, and that will dump a certain amount of electrochemical potential energy into the system by exciting one or other of these materials into an excited state. And that's then followed by a process of diffusion, where the exciton reaches an interface, and as it does so, it will lose some of its electrochemical potential energy through a relaxation. And at the interface, if everything works out nicely, we may have a charge transfer event, generating then some kind of semi-bound state with the charges still feeling each other's coulombic potential, but close to the interface, not yet free. They may then become free, possibly requiring energy or electric field to do that. And then once free, the charges could travel independently through the separate materials and make their way to the electrodes. And so as this goes on, we sort of are losing electrochemical potential energy to eventually end up with the amount of work that our charges can deliver to the external circuit, and that we would measure as if it were in open circuit, the open circuit voltage. So we have a process which is not completely efficient of photon energy conversion into electrical energy, and it's not completely efficient because at every stage there are some other processes competing with these driving processes driving us forward. Now, what I want to talk about today is not so much any element of this diagram, but it's really, I want to take this material, this sort of concept, and pick out some examples of how, over the past decade or so, we've seen materials design with the target of improving the function of such a device. And I want to then focus on how, with hindsight, it might be possible to sort of simplify the exercise of materials design. So let's go back 10 years. At this stage, I guess, Barry was maybe writing up his PhD. And the first roadmap was published by Marcus Sharber, who I think at that time was working in Konarka, for how the efficiency of a bulk heterojunction might depend upon the energy levels of the two components involved. And what followed, going really from the very beginning of the first sort of 2% efficient bulk heterojunction solar cell, efficiencies improved because of new materials. And we can track what happened, that first of all, a material that absorbed a bit too far in the blue was replaced by polythiophene, which is absorbing in the green, so it's better, it has higher mobility. And then we had a sort of a sequence of course, I won't show everything, but a sequence of innovation. So the optical gap of the material was reduced by using the concept of a push-pull heterojunction. And then it was recognized you need to do something to optimize, to try and minimize the energy that you pay, the energy that you give away at the heterojunction, and new materials were developed for that reason. And then work was done to improve the mobility, and finally to improve the way in which the materials could pack together. And at the same time, some work, but a rather more limited amount of work, has been done on improving the acceptor. And that's really sort of blossomed in the last couple of years with the introduction of some small molecular acceptors, which are really based on this push-pull concept used for conjugated polymers. So in the process of this kind of development of new materials, that led to efficiencies rising from 2% to maybe 12% in recent times. And it would be nice to say that all of this happened because we were following a roadmap, but I think it's not true at all. All of this happened largely because of trial and error. And so at different stages, things were done, and mobility was improved, optical gap was improved, the HOMO level was pushed down, the microstructure was improved, and so on. But these were things that happened, not really so much with design in mind, but with some development of new materials, trial, and then pursuing the ones that seemed to work well. And if we take what we know now and then think, how could we change the structure of the materials to get a better photovoltaic energy conversion efficiency, we could, in principle, address that question. Computational methods have come on. We understand to some extent what the physics and chemistry is at each stage. So you could start with some design of a material. You could simulate how the molecules would pack together. Having done that, you could then simulate electronic properties in the materials. And because for a solar cell, you need a heterojunction, we would also need to think about how materials would pack at a heterojunction, and then how the process of charge separation and recombination at the interface would occur on fast timescales. And having got all of that, you could then, to model the device, you would then need to try and extract some representative material parameters from these simulations, put them into a device model, simulate your JV characteristic, and then you could say, okay, this is a good one, this is a bad one. In principle, you can do that. In practice, you really can't. because there are far too many computationally intensive stages along the way, and some of the critical parts of this, like simulating a microstructure, make no sense at all unless you can validate the structure that you've got. So what you really need is a kind of iterative interplay between simulation and measurement at different stages. So this is a nice goal. In principle, you can do it, but you couldn't practically do it to design a new material for a better solar cell. So what we could do instead is we could try to simplify the question and then ask maybe if we want particular properties in a conjugated polymer, for example. I'll talk mainly about conjugated polymer. What are the critical properties what are the critical properties of the chemical structure for the physical property that I care about? So, for example, in the case of electronic properties, we might care about conjugation length. For optical properties, we might care about the transition dipole moment. Or if we're thinking about how a microstructure is formed, we might care about how the side chains attached to the polymer interact with their environment. And so what I'm now going to do is to sort of take us through a few examples of actually one of each, of studies that we followed, both experimental and simulation, where we try to clarify what are the sort of key degrees of freedom in controlling these properties. So I'm going to start by looking at the question, and it's a thorny question, of course, of what controls charge transport in a conjugated polymer. I've reproduced here an image that was published by Alberto Saleo, but really it's sort of representing the idea that charge transport is in a conjugated polymer is a product of two phenomena, and one is the degree to which the charge can delocalize along the polymer chain, and that will depend upon the conjugation length and also the intrinsic mobility, if you like, or delocalization along a conjugated segment. And it also depends upon the efficiency and the rate of hops between chains, and they will occur at the points where the chains can get close enough to pack efficiently. So the things that we're going to care about are the structure and the electronic structure of the individual strands of a polymer chain and the interactions between different chains when they come together. So this is kind of the space in which we need to work to understand charge transport. Now, one of the problems with charge transport is that because every conjugated polymer has got a gigantic conformational phase space, you can effectively prepare the material in a wide range of different microstructures, and different microstructures will express different electronic properties. And to give you an idea of this, this is a simple conjugated polymer. We call it polyfluorine. And here on the right, and this is a logarithmic scale, there is a collection of reported hole mobilities for that conjugated polymer. So along the bottom, we have some different measurement techniques. And even with a single measurement technique, you may find reports of mobilities that vary by orders of magnitude. So it's really quite a complicated problem. We can't easily start with that chemical structure and then explain why you can have almost any number you like for the whole mobility. So what we decided to do was to try to look at this and see, could we control the conformation of the conjugated polymer to try to make sense out of it? And the choice of the polymer is important, because in the case of polyoctyl fluorine, the polymer is capable of forming not only its natural kind of conformation, where you have a twist of about 40 degrees between the consecutive segments in the chain, but it's also capable of forming segments where you have a sort of quite a significant number, maybe something like 10 or more of monomers, which are lying in a metastable coplanar configuration. So they're completely flat. It's not the minimum energy structure, but it can occur, and it can be induced to occur. And we call this a beta phase. So we know how to introduce beta phase, we know how to keep it out, let's have a look at what happens to hole transport in the presence and the absence of beta phase. So we do the measurements of one of the most reliable measurements to access, or this is what we thought anyway, to access hole mobility is a time-of-flight photocurrent measurement, where you excite your film with a pulse of light, it sets up a transient photocurrent, you measure the time at which the current reaches the other side, charge reaches the other side, you work out from that velocity and hence mobility. So we do that, we compare a totally glassy polymer film with a film which has been prepared so it has some of these planarized segments in the chain, and we could see that introducing these planarized segments is reducing the mobility by around about 2 orders of magnitude, so it has a big negative effect. Okay, so we say it doesn't seem to be good news to have those planarized segments. Let's try some other methods. So we also looked at the mobility with impedance spectroscopy. You don't need to pay very much attention to these graphs here, which are showing the frequency the electrical response in frequency space, but the point is those data look actually quite similar. And when we extract a mobility from them, we find, okay, for this approximately quasi-steady state measurement, the mobility has been reduced by introducing the beta phase, but not by so much. We did another kind of steady state measurement using space charge limited current transport. Again, we find the same, the mobility or the conductivity is reduced, but not by so much. Okay, so in this case, the effect of beta phase is not so bad. And then finally, we looked at the literature where measurements had been done using a technique called transient microwave conductivity, and they found that the in-plane, they could probe the in-chain mobility effectively within a single chain or maybe within a conjugated segment. And in that case, they find that when they stretch the chain, which is like preparing it in the beta phase, the mobility is actually higher. So we put everything together, and we find, okay, 3 different measurement techniques. And whilst in time of flight, the beta phase is a real problem. It reduces mobility by 2 orders of magnitude. In steady state measurement, it reduces it a bit. And in the most local measurement of all, it doesn't reduce it, but it increases it. How can we make sense of all of that? So the obvious thing is to think about what this planarized phase is doing to the energy of the electronic states. And what it does is it's going to present a period where, an interval, where because of the strong conjugation between successive monomers, you have some stabilization of the hole. So the hole is going to prefer to lie in this stabilized segment than in this planarized segment than in the non-planar ground state segments that would be attached to it on either side. And so this planarized segment we could effectively expect to act like a trap. And if it acts like a trap, then it ought to be visible if we were able to probe the density of states. So we tried to do that with 2 different methods. And one of them, we took our transient photocurrents to a very large dynamic range. And in that limit, you can then sort of interpret your photocurrent transient as a density of states. So the response at long times ought to reflect the rate at which charge carriers are released from states in the gap of this material. And from that, we could extract a density of states. And doing that, we could see that when the beta phase was present, it introduced some extra feature below the transport edge of the relative to the glassy material. So it seemed to introduce a feature in the gap that was more or less what we expected. We tested it with another method, which a colleague in Bratislava, Wojtek Nadazdi, had developed, an energy-resolved electrochemical impedance spectroscopy, which is a method he could use to look at density of states in sub-band gap regions. And again, he saw a feature at around about 0.3 eV below the transport edge, which was, okay, it was present in both samples, but beta phase could easily have been introduced in transport, but it's stronger in the case of beta phase. So both measurements are telling us the beta phase appears to introduce a feature into the density of states some tenths of an electron volt, 3/10 of an electron volt below the edge. So having got that, could we then make sense of the measurements? And so we then needed a model. We can't use a normal device model that models drift and diffusion, assuming quasi-thermal equilibrium, because that wouldn't be able to reproduce the transient measurements properly. We had to use something where we have that resolution, but we can also assign an energy to the charge carriers so that any time we know where they are in the density of states. And we developed such a model, and then we could apply it to simulate both the transient measurement and the steady state measurement. And doing that, we could simulate the large effect of introducing these beta phase traps on the whole mobility in the transient measurement, and also the much smaller effect on the steady state measurement. So both of those results that had been seen in the experiment popped out of the simulation. The simulation was able to reconcile the apparently different measurements. And so if we look inside that and see what's going on, we can see that whilst in the case of, if we consider first the case of the simplest measurement of all, the transient microwave conductivity, not our measurements but others, here you're just probing conductivity within a segment. And when you have the beta phase segment, it's more planar, it would be more strongly coupled, the mobility is going to be higher. That makes sense. And then when we get to time of flight, what we found was that our photocurrent mobility measurement was not probing so much the average velocity of charge carriers through the film, but it's probing the rate of release of charge carriers from these traps. And if we look at what's happening to the charge carrier population as time advances, we could see that the strong feature that we interpreted as a transit time was really a release from traps time. And then, sorry.
Can I ask a question?
Yeah.
So in an earlier slide, you had shown mobilities measured by different techniques, and in particular, I think, field effect mobility.
No.
Was there a TFT?
Yeah, they're probably in the very first one here. Yeah.
And FETs, yes. And that mobility is quite low, whereas one would expect that technique to give you generally a higher mobility. And in particular, with this normal trap, you would expect the straps to be filled in the field effect transistor with, above threshold and so on. So, do I understand that wrong?
No, I mean, I think, so this is something that it's not easy to make an FET with PFO, because you have to get an electrode that will talk to the minus 5.8 HOMO energy of the polymer. So getting a suitable contact is not that trivial. We have done it, but we need to be absolutely certain that we are working with a perfectly glassy film. So this number is from the literature. It's not our number. And from the literature, it's quite likely that if people were not aware of the possibility that beta phase could be introduced during processing, that beta phase could be there and could be dominating the response. So this number, I cannot say whether beta phase is present or absent, but if it's present, it would explain why that number is not higher. Yeah? So the preliminary measurements, we've seen FET mobilities more around about 10 to the minus 2 when we think that the beta phase is absent, but we want to repeat that, and so that's why I'm not talking about it now.
Okay.
Is that okay?
Yeah, yeah.
Okay. And if you like, I've got much less confidence in the reasons for that number than I do for the ones that we've done in a more systematic way. Okay, so we were here, and then the difference between, if you like, the time of flight case and the steady state case is that in the one case, you're effectively looking at the change in charge density as a function of time, and so you're very strongly sensitive to the emptying of traps, and that introduces a large difference in the effective mobility. And in the steady state measurements, you're more looking at the average velocity of the charge carrier population, and in that case, the traps are a penalty, but not such a great penalty. So that then led us to an interesting question, which is how high might the mobility get? So we think from these timers of microwave conductivity measurements, and also ones that have been done very recently on a more planar polymer, and indocino dithiophenene benzothiadiazole copolymer, we think we have an idea how fast transport can be along the chains, and we think it can be fast enough to make the rate limiting step the jumps between the trains. So if we take that as a possibility, and then consider the rate of the interchain hopping step, and consider, this is for the case of the polymer I just mentioned, the IDT-BT polymer, we consider the strongest coupling between chains, we can make an estimate of how quick, how fast the mobility could possibly be. And my estimate is around about 10 to the minus 1 centimeters squared per volt second for steady state transport. But in other conditions, it may appear to be higher. And that would really argue that if we wanted to increase mobility, improving the transport along the chain is not on its own going to get us there. We need to do something about finding the conditions to improve the coupling between neighboring chains to maximize this rate limiting step. So that was the first study, and really trying to look at the effect of conformation on charge transport. And the next study also takes us to look at the problem of conformation of conjugated polymers. And this was the work that formed a large part of the thesis of Michelle Vesey, shown here in her rowing kit, because she was trying to get selected for the 2016 Olympics, and in the end she didn't quite make it, but at the same time she was doing this, so it was all quite impressive. And she's going to be examined next week. Her viva is going to be on Monday. So in the course of Michelle's thesis, we were quite interested in trying to understand the difference between two conjugated polymers. They're both diketopyrrolopyrrole thienothiophenene copolymers, but they have different length of side chains. We think the side chain would affect the packing, and we find that to begin with, we found the side chains had an effect on the performance of solar cells made from them. But when we looked more carefully, we found actually the difference didn't have anything to do with the side chain, really. It had to do with the molecular weight of the polymer. And what we discovered when we looked more carefully was that the thing that was changing when we changed the molecular weight of the polymer was actually the strength of the optical absorption, not the band gap, but the strength. So if you like, the oscillator strength of the primary transitions seemed to be increasing with molecular weight. And this was something that we found very puzzling. The thing that also made it quite interesting was that when we take the best of these conjugated polymers, it was showing, if we take the imaginary part of the refractive index and plot it, it was showing an extinction coefficient that was almost 40% higher than any other conjugated polymer that we had looked at with spectroscopic ellipsometry before there, and really giving us something which was almost off the scale of the family of materials we had studied before then. And so we then wanted to ask the question, two questions actually. First of all, why that polymer had such a high extinction coefficient, and secondly, why it depends on molecular weight. But for the moment, I'm just going to focus on the first question, because that by itself is interesting. And so we thought, okay, we know how to calculate extinction coefficient. If we know about how light interacts with polymers, let's have a go. We can calculate the transition dipole matrix element. If you calculate that, then you ought to be able to calculate the oscillator strength and calculate the real and imaginary parts, either of the refractive index or of the dielectric constant for the material. So that's known, it's basic physics. And then we could do the calculations if we do some electronic structure and then do some time-dependent density functional theory calculations to look at the excited states of our conjugated polymer. So if we take, for example, this is a dodecamer of thiophene, and we look at the excited states that we get using time-dependent density functional theory, this is the first and second and third excited state as you step up from the bottom. And you could see the first excited state has quite a high oscillator strength. The second one is completely dark because it's symmetry forbidden. And the next one is symmetry allowed, but it's not so strong. And we can go on and we could build up a spectrum. And this is on a log scale. And we see this is the visible region here. So as far as solar cells are concerned, it's clearly the first transition, which is the one that matters. So we thought, okay, it must be the case that our DPP TTT has an exceptionally high oscillator strength for its first transition. Let's compare it with the other materials that we know about. So we did that. And first of all, we look at the oscillator strength. And in order to normalize things and compare one polymer with another one, we look at the oscillator strength per pi electron and look at that as a function of the chain length. So we could compare the materials with one another. And the sort of slightly frustrating thing was that our DPP TTT polymer is more or less nowhere. It's not by any means the one with the strongest oscillator strength. But then we thought, oh, hang on a minute. These are wide bandgap materials, so oscillator strength is going to be high, but refractive index would then need to divide by the transition frequency. So let's have a look at the imaginary part of the dielectric constant instead, and that should then show us better the advantage of DPP TTT. So we did that, and here is DPP TTT, and still it's more or less nowhere. It's not by any means the strongest absorbing material. So we were a bit puzzled, and we then needed to go back and think again about the calculations that we'd done. And when we did these calculations, we prepared our chains in a way where we alternate. Typically, in our conjugated polymer, we will have a torsional potential that minimizes the energy of the structure when two neighboring monomers are either aligned in a trans or a cis configuration, and we had tended to align them in a linear fashion. But if that torsional potential is more or less balanced so that your polymer is just as happy to be like this or like this, they might also have aligned in a different way. And so we needed to consider both of these extremes. And when we did that, we saw that something rather interesting was happening in the case of the all cis configuration. So in the cis configuration, the polymer is going to be as bent as it possibly can. And it's going to become, if you like, more bent as the chain becomes longer. And what we were seeing was that the specific oscillator strength rises, and then it turns over. And it turns over at a different place for the different chemical structures. And that's all got to do with the geometry of the individual monomer. So if you have depending upon the collinearity of the polymer, what is the angle of deviation between one monomer and the next, and the degree of bending as you make the chain longer will change. Okay, so what's happening? So if we have the chain as long as it can possibly be, that's going to maximize the transition dipole moment of the first transition will generally be aligned along the polymer chain. And that would be maximized for a linear configuration, for the most linear, in this case, the trans configuration of monomers. And if our chain then becomes somewhat bent, the transition dipole moment of the first transition will be weaker, and it will tend to give up some oscillator strength to higher lying transitions that would, in the linear configuration, be symmetry forbidden. So we could then see some oscillator strength being passed from the first transition to higher transitions, and we see this in the calculations. So this we could kind of quantify through the concept of persistence length. The concept is illustrated here. We could think in a simplistic way about adding up the dipole moments of the individual components and getting a result which will depend on the overall conformation of the chain. And when we take into account the geometry of the molecule, but also the depth of the two potential wells for the cis and trans configuration, we could make an estimate of persistence length. And we could see, when we measure the persistence length in terms of chain length, amongst all the materials that we looked at, our hero polymer, which was the DPPTTT, had got by far the highest persistence length. And if we pick one of the others, which compares reasonably well for the trans configuration, but we take other conformers into account, its persistence length is much weaker, and it also had a much weaker absorption. So all of this seemed to sort of support the idea that the collinearity or the persistence length of the polymer is something that could enable a stronger optical absorption. So we tried to get this published, and a very, I suppose I'm going to say helpful at this point, reviewer came back and said, okay, why don't you show it for something else? So we thought, okay, let's see if we can show it for something else. And so we were quite lucky because we found two something elses. One which is actually a close relative of the first polymer. It just has a different configuration of thiophenes in the side group. And then the other one is one of these IDT-BT polymers, which I mentioned before, are very rigid. And we were lucky enough to have samples of different molecular weight of at least of the IDT-BT. And then we went off and measured them, and I can say we were absolutely delighted to find that both of these polymers, which ought also to have a high persistence length, also displayed a strong optical absorption, and so that at least supports the idea. So the concept that we then have now, and of course, you know, this is out there, that can be tested, that can be refuted, but the idea is that the strength of the optical absorption in a conjugated polymer should depend upon the simple concept of the geometry of the monomer and the torsional potential that controls the likely sort of ensemble of conformations that polymer will adopt in a statistical ensemble. So a simple concept that would help us to access an important property, which is the strength of the optical absorption. Okay, so I have one more topic. Barry, shall I march through? We've got 5 minutes to 5. Yeah?
Sure.
Yeah? The final thing, and it relates to, I'm not going to dwell on this, but it relates to the idea that when you photoexcite your binary system, you have a polymer, you have a fullerene, or you have two components with an interface at which charge transfer can occur. Now, we have a certain amount of information from literature, from spectroscopic studies, theoretical studies, and others, that this efficiency of this charge energy, well, the evolution of the photoexcited excitonic state into a pair of separated charges, the efficiency of that process, when we have a binary polymer molecule system, the efficiency tends to be enhanced whenever the small molecular phase, normally the fullerene phase, is able to crystallize. So that was the point I wanted to make here. And I'm not going to go into the physics of charge separation, except to say it's a very interesting area, but it is dependent upon the microstructure of the system. And then we have the question of what is it that controls the microstructure. So the first point is that when we work with a binary system, the properties of the blend is what matters. It's not the property of one component or the other, and the properties of the blend are different from the properties of the individual materials. And if we think about what property of the blend we want, for example, for a solar cell, we require a certain degree of percolation through the small molecular component, but we also require a certain degree of mixing. And the consequence of this is that the optimum composition is one which is slightly fullerene-rich relative to the point at which the interaction between the two components is the strongest, which we would call the eutectic point. And if we then wanted to find this composition in AN other material system, we would need to understand what it is that gives rise to those reactions, those interactions that make the components mix and control the miscibility of one phase in the other. So this is a work that we were addressing using a technique of quasi-elastic neutron scattering, which is a method not so easily accessible, but once you have access to it, you can learn quite a lot. And quasi-elastic neutron scattering will give us access to the dynamics of side chains and backbones on a time scale really that's somewhere between sort of nanoseconds and femtoseconds. So you get data out, but what we were also able to do, and this was the work of Anne Gilbert in my group, was we were able to at the same time make an atomistic molecular dynamics study of the different systems that we looked at. And so we carried out a detailed study where we looked at the sort of the very well-studied binary system of poly-3-hexylthiophene and PCBM. And the thing that we found from so our strategy was this. So with neutrons, you see hydrogen. And if you want to look at one component and not the other one, then what you ought to do is deuterate the component you're not interested, and then look at a blend, which you hope will be more or less structurally identical to the hydrogenated version. So if we look at a blend with deuterated PCBM, we see the polymer. We look at a blend with deuterated P3HT, and then we can see the fullerene. So we did that, and then we could ask the question, what happens to the dynamics of those molecules in the blend whenever you put them into the blend? And the answer was quite interesting. So when you put fullerene into a polymer, it slows down the dynamics. So fullerene frustrates the polymer. When you put polymer into the fullerene, it actually makes it easier for the fullerene to move. So the fullerene effectively acts as a plasticizer for the polymer, whereas the polymer effectively vitrifies the fullerene. So this is very clearly saying that the properties of the blend are not simply the sum of the properties of the individuals, but they have a specific interaction. And so with the MD, we could reproduce the QENS results. I don't show that here, but I want to show a nice kind of result from the MD, which was that when we look in detail, we found that there seemed to be a kind of specific molecular interaction between the fullerene and the polymer in such a way that the fullerene is tending to bring the thiophenes in a cofacial arrangement where they're more likely, the first layer of polymer outside the fullerene shell is more likely to be organized in a cofacial manner relative to the fullerene. And we could do this by looking at the sort of the effective radial distribution function for that angle, if that makes sense, kind of an order parameter for the cofaciality of thiophene relative to fullerene, and we could see there seems to be an interaction. So to put it into simple language, the polymer, the pi conjugated part of the polymer, is wrapping around the fullerene. So there is here a specific chemical interaction which kind of makes sense of the fact that the polymer, the amorphous part of the polymer, is frustrated, it's slowed down by the presence of a fullerene in the blend. And then we could build on that to go on and then say, why is immiscibility such and such? How might you change the structure to have a different degree of miscibility? And that's, of course, something that would be interesting to do. The thing I would then want to finish on is a very final example, which is touching on the same concept of where we have the same polymer as in the previous study, but then using, instead of a fullerene, we used these alternative acceptors, and not one, but a combination of two of them in a different ratio. So we call these non-fullerene acceptors. And typically, if you have a ternary system, you have a polymer and then you have something else, and you change its properties linearly, you think linearly from one regime, in this case, higher band gap to lower band gap, you might expect then a monotonic change in the properties that result. So from the solar cell, we could see as we put in more of the higher gap component into the lower gap, we would monotonically change the JSC, and that is perfectly following what happens with the optical absorption. But what happened with the open circuit voltage was slightly more interesting because it showed two phases. It shows a jump up, and then it stabilizes, and then it shows another jump up. And because of this kind of non-monotonic behavior of the VOC, we have as a result, because efficiency effectively reflects current times voltage, there was a peak. And so there was a composition of the ternary which was better than either of the terminal points, and the solar cell efficiency was better. And why was that? And the reason has all got to do with the specific interactions of these different fullerenes with the polymer. The lower band gap fullerene is something which interacts strongly with itself. It likes to crystallize. But as you add the alternative acceptor to the blend, then what you do is you vitrify the first and eventually break up the crystals. And as you do that, this will have an effect on the band edges, on the HOMO and LUMO energies, and that gives rise to this trend in VOC over the first phase. So over this phase, we have the breaking up of aggregates with the concomitant breaking up of the extension of the electronic states. So that will raise the band gap and raise the Fermi level. And then when you get past that point, you simply have an amorphous mixture. And what you observe in the VOC is the trend that you would expect from an alloy, a simple alloy of one thing in the other, so that at the very, very extreme of one component, you shift to the higher band gap limit. So this is what we think is going on. And that was a rather... it looks like hose pipes to me, but my colleagues generated this image to try and illustrate what's going on in terms of you've got one component with a specific interaction with itself is weaker compared to its interaction with the other components, and then it serves the purpose of kind of controlling the microstructure. So it's just an example of the sort of thing that could be possible if we understood these specific chemical interactions. So finally, I can finish. And just to come back to the very first point, the point was that we have a role, I would argue, for material science in addressing a wide range of problems which are relevant to the future of energy supply. I've been talking about molecular electronic materials, and I've been trying to show how if we can understand our materials well enough to be able to identify the kind of the critical degrees of freedom, then we could simplify the design problem. So looking specifically at the case of charge transport, I was arguing that intra-chain transport and molecular packing are important. When we looked at optical absorption, I argued the persistence length is an important simple parameter. And then when we look at the rules that control the packing of molecules in a binary system, I would argue that the specific sort of chemical and physical interactions of the molecules close to each other are going to have an important role on the behavior of the polymer of the system, binary system as a whole. And I will finish by thanking my still intensely European research group and you for your attention.
you implied that playing the sort of games you've been talking about could increase the efficiency of a cell to something like, I think 10% was the best number you showed.
But yeah, about 12.
But the target value needs to be at least twice that now to make it a viable device. Is that correct? And the other point always is, how do you make acres of this polymeric system with properties which have whatever your best results are?
So, I mean,
They're unfair questions, but...
Yeah. I mean, to answer the first one, I mean, what I was trying to say at the time was I present this, you know, I make the point that a carbon-based system, for example, has got low costs, both in terms of the availability of the materials and the processing, which is important. You have a low energy return over investment, and this is something which matters in a variety of applications. So in the case of solar cells, there are other materials that have a higher efficiency, and other things have happened in the photovoltaic market that mean that the cost of the module is not as important as it was some time ago. But I wasn't, but what I was saying, the point I'm really trying to make is that there is a case for understanding the material science of materials which could play a role in solving the problems of making clean energy available at a lower energy cost. I'm not saying this is the answer. When we get to the acres, you know, you can ask the same question about, you know, any other semiconductor. And with silicon, we had 50 years to do it. And with 50 years, I'm pretty sure we could do it with another material, whether you would actually want to do that or not. You may want to use it in a different way. But, you know, this kind of area, I mean, you always, at the early stage of a technology, you always have a drop between the efficiency of the hero device and the efficiency of the thing that you try to make against a commercial protocol. And as time goes on, that gap reduces. So all I can say is you try and see if it works or not. But I wasn't trying to sell this as the answer to the energy problem. What I was trying to say is that there's a place for materials research. And number two, that in the materials research, if you can try to identify the design problems that are relevant for the property you care about, you might be able to short circuit some of the trial and error that takes time. Okay.
Thank you.
I have a question about, well, I have two separate questions on the first one.
Yeah.
I'll see if there's another question before I jump to the second, because they're totally separate ideas. One is about the increased absorption with the conjugated polymer chain. Is there any analogy you can bring from that learning to other properties? Like, will a similar change of the micro or nanostructure of the polymer chain also imprint on things like mobility or exciton binding energy or the ability to do charge transfer, things like that?
Well, for sure it will impact on the mobility. But that's something, if you like, that would have been known. We didn't expect what we found with the optical absorption. We didn't expect. I was absolutely against the idea that it could have anything could have affected the optical absorption. So, yeah, I mean, so improved. You know, I mean, you get win-win with various things. With the IDT-BT is a good example because it's a highly, you've got a high degree of linearity just because of its geometry, not particularly because of the torsional potential. And it also has a high mobility, and it also has a high optical absorption. So, you know, stiffness in the polymer chain is quite a good idea, but then it needs to be compatible with the processability. Yeah.
Okay. Jeff, before I ask that.
Sorry. When you have this thing out in the sun in a practical sense, the temperature is going to be changing like crazy. So do you have to, if you're going to design a molecule, do you have to design essentially a conformational lock in it so that as it warms up, the performance of the device isn't going to change, for better or for worse?
The short answer is yes. And yeah, I mean that's been known. If you have for example, a low TG polymer, you would, after a period of operation, you begin to see the migration of the small molecular component to make clusters.
In terms of these conformational arguments.
Mm-hmm. Yeah, yeah. So in terms of the conformational arguments, I mean, the persistence length will still be to your advantage, because the persistence length is a kind of a measure of the limits on the conformational, the change in extension with conformation. So I would say that if you want to operate at higher temperatures, it would be at a very, very, very simple level to your advantage to work with something with a high persistence length. But, you know, I mean, I would say other things are going to go first. You know, like the binary microstructure is probably going to go first if you heat up.
So my final question, and then we'll get to this one, was about back to the beta phase polyfluorine.
Yeah.
You talked about how the beta phase can introduce traps.
Yeah.
And you also talked about how the beta phase, because of its more planar structure, has better intra-chain transport.
Within segment, yes.
Correct, with the microwave conductivity you mentioned.
Yeah.
But I can also imagine that the planar structure would have better interchain because of better pi-pi overlap. And you didn't see that because of these added traps. But what about the sort of trap-free mobility that can be extracted? Do those still show that the beta phase PFO has better mobility intrinsically, like in the trap-free limit, compared to?
Not really, but I think there's an explanation for that, which is that you only get beta phase if you've got octyl or nonyl side chains, and the side chains are believed to be kind of extended along the polymer, so they're probably in the way. Yeah.
Okay.
The big beta phase is not. Well, there's argument about it in the literature, but some schools will argue that the beta phase segments will appear in isolation, that they're not. They certainly do not seem to be the result of aggregation. I mean, it's a good point. And then the other thing which is really interesting about the beta phase would be that if you could introduce, rather than 5 or 10% of beta phase that we could do, if you could introduce 50%, you could have something really speedy. But it would then depend on exactly the thing you said, which is how good is the coupling between the two. And I think there's not enough evidence to really answer it, but we don't see the trap-free mobility getting better with beta. She gets worse.
Last question over here.
Yeah.
This might be a very naive question, but are there any lessons that can be learned from studying abiotic systems like this one that can be applied to the study of biological systems like plants and photosynthetic bacteria?
I would say probably yes. I mean, it's there are other people in the audience who could answer that question much better than I could. But just to let you know a bit about where we're going, where we've actually recently been studying conjugated polymers as photocatalysts, and they show some very interesting properties. And I mean, amongst the properties that are interesting, apart from the fact that you could access a relatively sharp band gap and strong absorption, you also have the possibility to sort of, by playing with side chains and backbones separately, you have a possibility to sort of tune the interactions, so that you could have something which is hydrophilic, something which is hydrophobic, and then try to control different parts of the system by playing with the chemical structure. So this is not a biological system, but it's performing a function that in another context a biological system would perform. And so my guess would be that sort of the lessons that you can learn from the effect of the molecular structure on the optical and electrochemical function are quite transferable. Okay.
Okay, we have a reception outside.